All right, so we're going to start in on some IXL relating to solids. And this is grade 8, U.9, and it's asking about the surface area of pyramids. Whenever you see surface area, it's the same thing as the total area. What you want to be careful of in this unit, though, is that we'll learn a lot of formulas that relate to total area or surface area. And you always want to remember that surface area in any question isn't always restricted to a formula. You always have to look at the object and decide, okay, let me visualize what is the net of this thing, and can I apply a formula here? Do I need to adjust that formula? And if so, which is the right formula to use? So again, surface area, total area are really the same thing here. So in this one, it says, what is the surface area of this rectangular pyramid? We're going to start first by doing it one method where we'll just turn it into a net. And remember, a net is just a representation of the shape, that this is meant to be a 3D shape here that you're seeing on your screen, and we're going to turn it into a two-dimensional representation of the same shape. Because if we're trying to find area, not volume, which is a three-dimensional thing, we're trying to find area, we have to say, well, if I flatten this out, how much area would that flattened out version occupy? And so for this pyramid, a good way to draw the net of a pyramid like this one is to start with the base in the middle, right? That base can be a triangle, it can be, in this case, a square. Even though it says rectangular pyramid, it happens to be a square because, all squares are rectangles. You could have a pentagon, hexagon, whatever it is, as your base of your pyramid. Now, in this case, the base is a square, so we're going to start off by drawing a nice square here, and that is my base. And then each side of the base has to have a triangle coming up from it. So it's almost like drawing a little star here. I'm going to draw a star. You see, well, actually, first let me just label here so we can keep track of our dimensions. Each side of this square is 3 centimeters. So let me place a little 3 here just to remind myself that that's what these distances are. Now the triangle coming off it, it's got to share, it's the base of the triangle has to share the edge of the base here. And I'm going to have the triangle go up from the base like this. And these triangles, I'm doing a pretty inexact job, but all these 4 triangles would be exactly the same, which can come in handy because you can say to yourself, if I have to calculate the area of these triangles, I could just calculate the area for one of them, then multiply that by 4. Now, the side of these of the base here, there's 3 and 3. The other dimension that we need for this triangle to calculate the area of a triangle, right? You don't necessarily need the side lengths. You always need the base of the triangle when we're using this as our base of our triangle, and the height of the triangle. So if you look in the diagram, it doesn't actually tell you how long the side lengths are of this triangle here, right? It also doesn't tell you the height of the pyramid from the foot of the height in the middle of the base all the way up to the apex here. It doesn't tell you that. What it does tell you is the distance from the apex of the pyramid down to the middle of the base of this triangle here. And that distance here is your slant height. So that's terminology you definitely need to know. And for this diagram, we want to have that as well. That slant height here, as we can see in the diagram, is going to be 6 centimeters. So let me put a little 6 in here. Now these are all the numbers we need to be able to calculate the area of this flat shape now. Really, this has gone from a 3-dimensional problem to now our problem is just what's the area of this here, right? Like if I colored this in green, this isn't going to work very well, just so you see what I mean. If I wanted to know how much green there was here, that's really what the question's asking me. What's the surface area? I don't care how much space it occupies. If it asked me about the volume, then I'd have to calculate that. But in this unit, over and over, make sure you know, is it asking me about area or about volume? Is it asking me about how much green or how much space this occupies? Here, this question, because it's area, this is how much green. So in order to answer that here, this isn't too difficult. I got to get the area of the square. And this square's got sides of 3, so to find the area of a square with sides of 3, let me go back to conventional color like black here. I'm going to do, well, it's going to stay green. All right, 3 times, let me use a little multiplication, 3 times 3 would give me the area of the square. And I have to add to that an area of this triangle, and so it's going to be base times height divided by 2. So it's going to be base times height divided by 2 will give me the area of one of those triangles. And so 3 times 6 divided by 2 will give me the area of that triangle. But since there's 1, 2, 3, 4 of them, I can just put a 4 in front of this and multiply the area of my whole triangle to get the area of all 4 of them together. So I'm getting the area of the base here, and then I'm adding to it the area of those 4 triangles, and that's going to give me the area of my pyramid. Now, I'm gonna do the calculation here just so you can see it. 3 times 3 will give me 9, and then if I do 3 times 6, which is 18 divided by 2 is 9, times 4 gives me 36. So all of those triangles together gives me 36, and if I add those together, I get a final answer for the surface area, which is the same as total area, 45. So let's put 45 in here just to show you that it's right. Okay, now before we go on to this one, I just want to come back to what we just did, okay? Because we're going to do something very similar with this one here, right? It's another rectangular pyramid, another square pyramid. When we did the 3 times 3, that's the area of the base. And this, excuse me, this here, the area of one triangle times 4, that is the area of all the lateral faces. Those triangles in a pyramid, those are your lateral faces. And together, all of that is what we call the lateral area. So it's the area of the base plus the lateral area. And you'll see there's a shortcut we'll do here. This might remind you of something we saw in the polygons unit. This 4 times the 3 will always, like the number of triangles times the base of each triangle, will actually always give you the perimeter of the base. So one way that we think of this formula here, we have area of the base, which could be a square, could be a triangle, whatever it is. That doesn't have a set formula. It just depends on what you're dealing with. Plus the lateral area is always perimeter of the base times the slant height, because that height of that triangle, that's your slant height. So your formula here for lateral area, that's all the triangles together, is always perimeter of the base times the slant height divided by 2. Okay, the formula is catching them right now. I really want to make sure you guys get the instinct of being able to recognize the nets, so we'll focus on that for now. Let's do another example. Actually, I'd like to do a triangle one, so I'm gonna do this one real quick using that formula, and then it might seem like it goes fast, but it's just because I want an example with a different shape. So 5 times 5 would give me the area of the base is 25. The perimeter of the base is 20 times the slant height is 160, gives me 80. So this is going to give me 105. Okay, here we go, a triangular pyramid. So now we can work with a different net here. Okay, in this one, we're still going to be doing perimeter of the base. Like for the lateral area, it's still going to be perimeter of the base times the slant height over 2. And we're still going to get the total area, the surface area, by doing area of the base plus the lateral area. If you're not quite catching that, then remember, the most important thing, break this down into a net first. So what does this look like flattened out? Okay, let me make sure I've got the right colors. Nice purple here to match what we have in the diagram. So this, if I flatten it out, I've got the base in the middle, which happens to be a triangle. So let's draw that. Got a nice triangle in the middle. And this triangle has side lengths that are actually all equilateral. You see, this is telling me 2 millimeters here, 2 millimeters here, 2 millimeters here. So the side lengths of this triangle are all 2 millimeters. It's a nice equilateral triangle. And then this is telling me that the height of the base, right? Not the base of the height or the foot of the height or anything like that. This is the height of the base, just the height of that triangle that's at the base. And I'm showing you this is meant to be the base of the shape here. The height of that base isn't 2, it's 1.7. Right? It makes sense that it wouldn't be 2 because look at here, right? If this whole side is 2, then this is 1, this is 2. This is a hypotenuse of 2, a leg of 1. Pythag, you could actually calculate that 1.7 on your own, but it gives it to you here in the diagram. So this is my base. That's at the bottom. And then spreading out from that, I've got 3 triangles that come out. One for each side of my base. And then these 3 triangles go up. Now you might say, well, shouldn't you have drawn those as equilateral? One, I'm not very good at drawing with this tool, but these are actually not equilateral triangles. You might look at it and say, well, doesn't it say that their sides are 2 millimeters? No, it doesn't. It doesn't tell you at all what the side lengths of this triangle is. It tells you the base of this triangle here is 2 millimeters, but it doesn't tell you how long that is, or how long that is, or how long this is. What it does tell you, this dotted line here is 2 millimeters. But that dotted line isn't a side of the triangle. I'm going to draw it into the diagram here. That's how long it is from the base to the apex, right? From the middle of this edge up to the apex. And that is called the slant height. And the slant height is 2 millimeters. Okay, and we'll see that for calculating surface area, the slant height is more important. We don't actually need to know how long these sides are. These aren't equilateral triangles. Doesn't really matter. It's not that important. What I need is the information to be able to calculate the area of the base and to calculate one of these triangles, which I can then multiply by 3. Right? So the area of this triangle at the bottom, it's going to be 2 times 1.7. And then since it's a triangle, I'm going to divide it by 2. Right? This is the area of the base, 2 times 1.7 over 2. And then to get the area of the rest of these, let me start by getting just this triangle here. This is one of the lateral faces. Remember, lateral faces are those faces that are not the base. So it's going to have 2 times 2 divided by 2. 2 times 2 divided by 2. So 2 is the base of my triangle. 2 is also the height of that triangle. And then base times height over 2 is your formula for the area of a triangle. This 2 is just the base of that triangle. This 2 right here is the slant height, the height of this triangle. And then that over 2 is just because it's the formula for the area of a triangle. So 2 times 2 over 2. But you're saying, well, that would just give you the area of this one. Aren't there 3 of them? Yes, you're right. So I've got to say, if I want the entire lateral area, I want to multiply that one area of a triangle by 3, like this. And then once I've got this lateral area here, I'm going to add it to the area of my base. So 2 times 1.7 over 2, if you put that in your calculator, 2 times 1.7 is 3.4, divided by 2 gives you 1.7. 2 times 2 gives you 4, divided by 2 gives you 2. 3 times 2 gives you 6. So here I have 1.7 plus 6 to get my surface area. When I add those together, I get 7.7 as my answer. Oops, 7.7.